Alright, so this is Earthquakes Part 1. Starts off with 3 quiz questions for you to look at, give it a shot. If you have any questions about the answers, feel free to email me or we can talk about that on Tuesday. We'll get into earthquakes. Again, it's broken into 2 parts, so we won't necessarily look at location in this first part, but look at detection and prediction. Alright, so obviously we live in an area where it's not as earthquake prone as other parts of the world, but as you know, there's massive damage associated with earthquakes. And for that reason, it's a good link to looking at plate tectonics, which we're going to do next. So a lot of people would teach plate tectonics and then earthquakes and volcanoes, and I've tried it that way, and that's fine too. I thought this time around we'd look at sort of some of the consequences of plate tectonics before we get into that. Alright, so this link shows the number of active earthquakes on the planet at any given time. You can see that there's around 50 earthquakes per day around the world. Most of those are unnoticeable in terms of the Richter scale magnitude, which we'll talk about later. The largest, just because a lot of people ask, was a 9.5 magnitude earthquake out of a scale that goes to 10 in Chile in 1960, and that's a pretty devastating earthquake. Alright, so there are some things that people have tried to use to predict earthquakes. They're not 100% accurate, but these are things that people have noticed happen prior to earthquakes. The first is change in rocks. We've noticed that there have been small cracks that start to form in rocks, which cause seismic waves that move through the earth to behave differently. This sometimes results in foreshocks or small seismic events that happen before the earthquake. Because those small cracks open up, water can seep into those, so the groundwater level decreases. You would notice that in a well. Those cracks also can release radon gas, so an increase in radon gas levels. And then finally, as I said, the seismic waves, how they move through the earth changes, and that's really a function of the density of the rock. And so as the rock breaks up, it's less dense, and the first 2 seismic waves, the P wave and the S wave, arrive differently than they would under different circumstances. Right. Because there's so many earthquakes that occur on a given day, we have sort of a record of how those waves move through the earth in any particular location. The second category is what we would call seismic gaps, which probably is better described in a picture. These are, if you look at a segment of, just skip to the next slide here. If you look at a segment, each of these little dots that is in red represents an earthquake. A gap then is a location where there have been earthquakes in the past, but not a lot recently. And so in this particular area, you can see that there were 3 gaps that were identified. The next earthquake was the Loma Prieta earthquake that was in, I believe, 86. This is one of the ones that I remember because it happened during the World Series baseball game. It was televised, and they had to remove everybody from the stadium because of the threat. We've also long noticed that animals behave differently. You probably know that if you have animals. Again, not 100%. None of these are. Hard to determine if the animals are just acting squirrely for another reason, but we do know that animals can pick up, they can sense something. We know that they see in different wavelengths, they can hear in different frequencies, different smells. Not quite sure what it is. And then finally, statistics, a lot like the seismic gaps, looking for locations where earthquakes have occurred in the past but not recently. So the idea basically is that if an earthquake has occurred somewhere, or we know there's an existing fault, the longer that energy is building up at the fault, the more likely that that's a location for the next earthquake. There are some things that we can do. We can't stop earthquakes from happening, but we can try to mitigate or reduce the severity of them. So we now know that with planning and zoning, we could require houses and buildings to be built a little bit differently in earthquake-prone areas, which is good. The downside is in regions like ours, we don't have codes for these kinds of things. So an earthquake that could occur in this region could do a lot more devastation because we don't plan for them here. But in earthquake-prone areas, these are some of the ways that people try to mitigate the damage that's done. So a lot of the damage that is done is due to fire. Obviously, gas lines break, electrical wires break. To sort of compound that, then water mains break and water not available to put out fires, landslides. All right, let's skip over some of this. This particular map shows regions where you're more likely to experience an earthquake. Note that we're not, we are, in an area. It's not the highest area, but you can notice that there is a hazard here. Every once in a while on the news, you hear of an earthquake, usually kind of small. But these are not well understood. We're not along a plate boundary. So we'll look at categories of earthquakes, but we don't fit in some of the main categories. All right. In terms of expected loss, another map, some of these areas you probably already know, where there's major fault zones that go through them. Again, we're not completely out of the woods in our region. There is some expected damage here. So we haven't had in our region large earthquakes like this. Those are usually around magnitude 2 or maybe up to the 3. I haven't looked at the record for our region, but they're usually pretty small. Larger earthquakes obviously do much more damage. I'm going to let you click on that. I'm not going to go through it here, but liquefaction is one of the things that can happen during an earthquake, where the solid ground starts to behave like liquid ground, and this actually can cause buildings to slowly sink in to the ground, so that increases the amount of damage that's done. So there are foreshocks, which we just talked about, that happen prior to an earthquake. There's the primary earthquake, and then there are aftershocks that happen up to weeks after the main earthquake, depending on the magnitude, the amount of energy. And these can be really devastating because a lot of people want to go back into their buildings, homes, to see what kind of damage was done. These aftershocks persist for days and can be devastating to an already weakened building. All right, so this shows again that Loma Prieta earthquake. See in the graph here that the number of earthquakes or aftershocks decreases over time, starting with somewhere around 70 per hour. If you look at the sheer number, 4,760, most of these are not felt, the vast majority of them, but we have 2 that are magnitude 5 on the Richter scale, 20 magnitude 4s, and then 65 3s that are perceptible but probably aren't going to do that much damage. But again, these are after the structures have already been weakened. So aftershocks a major source of concern after the primary earthquake. All right, we already kind of mentioned this. Skip over that slide. One of the things that can happen to large high-rise buildings is what we would call pancaking, and this is what we've seen in some of the pictures so far, where the ceiling basically is now touching the floor of a multi-level building. It just kind of falls straight down. There is some swaying that can happen, and actually buildings are meant to sway. There's a good bit of sway, especially in a skyscraper. The top of the skyscraper is actually meant to sway, many feet in any direction to so that it's not as rigid and will snap. And then buildings now are made. Some of them have a large ball bearing that they move on, and so there's a lot of engineering that has happened. Some have weights at the top that if say for example the wind's blowing, or not the wind, but they do it in the wind too. But if the earthquake is moving towards the north-south, it will, as it's shifting south, the weight on the top will shift to the north, and so on, to sort of counteract that force. Just quickly about tsunamis. So tsunamis are also associated with earthquakes. They're associated with other things besides earthquakes. But when an earthquake disturbs the ocean floor, it basically creates a fault. The water rushes in to fill that void that has been created, and it sends waves out in all directions. Those waves first pull the water out to the ocean and then come inward. You can see the devastation here in Indonesia. And so this is what's happening. This thrust fault drops part of the ocean floor. The water rushes in to fill that void, and that sets up a wave that at sea has a long wavelength but a short height or amplitude. And as they get closer to the shore, the wavelength decreases and the wave height increases. The same thing that happens with any wave that comes into shore. It's just in this case, the initial wavelength is so large that as it gets close to the shore, the wave height can be very, very large. Lucky for us, the travel time is pretty significant from getting from one area to another. And you can see that an earthquake, if it occurred in this location in Alaska, would take around 10 hours to get to New Guinea. So now we have warning devices in place that should be enough time to get people to higher grounds. You can see that even the Hawaiian Islands, about 5 hours away, would have enough time for people to evacuate to higher ground. All right, and so here's just a picture of a mosque left behind after a massive tsunami has arrived. All right, a couple of terms that people sometimes switch around. The first is focus. This is a place within the earth where the rock first breaks. This is usually beneath the surface, but it can be anywhere from the surface to about 435 miles deep. Any deeper than that, and the temperature starts to increase, and those rocks are more plastic, so they're not going to snap. They're going to bend more than break, and so they don't release the amount of energy that we would expect with an earthquake. Most of the earthquakes that do occur are what we call shallow focus earthquakes, and so earthquakes are broken into really 3 categories: shallow focus, medium focus, and deep focus. Here I'm just focusing on shallow and then lump the others into deeper focus. All right, so the downside of this is because they're closer to the surface, the energy doesn't have to travel as far to reach the surface, and so these can do more damage given, all other factors being the same. All right, so that's the focus. It's within the earth along the fault zone where the fault is moving. Above that then is the epicenter. The epicenter is the place on the surface of the earth that is directly above the focus, where we would say the earthquake has occurred. All right, so on the news, if you hear that there's an earthquake somewhere, they would say, either the name of the town or something like 20 miles southeast of San Francisco. To tell you where the epicenter is. All right, the elastic rebound theory is the theory that describes how earthquakes occur. Basically, the idea is that there is a stress that's building up in any given area along a fault. That stress builds up, and then eventually the material breaks, and that results in an earthquake. This is a simplified version that has the period between each of the earthquakes being stable. In reality, that's not the case, and how the stress builds up can vary. But this is basically what it looks like, and we can just mimic this with something like a pencil, where basically the rock is building up stress, and then eventually, once the stress overcomes the strength of the material, it's going to break. And so that's what's happening here in the diagram. We have a fence here that is a reference point, and the stress builds up, and eventually the rock is going to break and snap, and so the fence will move. And then the rebound part is that it sort of settles back in towards its original position a little bit. And here we have the actual picture of that. Someone obviously didn't build a fence this way. We can see sort of the fault here running through the ground. All right, in terms of categories of earthquakes, there are a couple of ways earthquakes can happen. 90% of all earthquakes occur along plate boundaries. And so there's really 6 types. Divergent plate boundaries, where 2 plates are moving apart from one another. These tend to be a little bit less powerful. Just think if I gave you like a piece of taffy to share with somebody, pulling it apart is an easy way to break that taffy. So these don't release a lot of energy. Convergent, 2 plates moving towards one another. Again, we'll come back to these when we talk about plate boundaries. But these happen at subduction zones, which we'll get to in detail next week. And these are more shallow earthquakes, but also produce deep earthquakes. So here's a map of what that would look like as the plate is diving under another one. It sort of goes in at an angle, and we can see this in terms of the depth. As we move away from this, the depth changes. All right, transform fault boundaries. These are 2 plates sliding past one another. These are the major earthquakes that occur. This is the San Andreas Fault out in California. These 2 plates sliding past one another. And then there are plates that happen, or earthquakes that happen within a plate, and then within a continent. and I'll stop.